So we're going to look at how to graph rational functions. So in this video I'm going to go over various cases for rational functions. So let's look at an example here. We've got a rational function f of x. So when you're analyzing a rational function, the first thing you usually want to do is factor the numerator and the denominator. Now in this particular example, the numerator and denominator are already factored. So that's sort of already taken care of for me. So now I'm going to make any cancellations that I can. These two factors of x minus 3 would cancel. And I'm going to rewrite the function after those cancellations. So I would have the numerator would be x minus 4 times x minus 1, and the denominator would be the quantities x plus 1 times x minus 2. So now those factors, that factor of x minus 3 that I canceled out of the numerator and the denominator, that's going to produce a hole in the function. So to determine the location of that hole, well, I would just look at sort of the factor of x minus 3, what would make that factor 0, and that would be 3, an x value of 3. And now I'm going to evaluate sort of the simplified version of the function to figure out where the y coordinate would be located for the hole. So notice that I can evaluate the simplified function, but what I need to keep in mind here is that the function itself had a factor of x minus 3 in the numerator and the denominator, and I would not be allowed to evaluate the original function at x equals 3. I could evaluate the simplified function at x equals 3, and that tells me where the hole is located, but I need to put a hole on the graph indicating that there is no point there, because an x value of 3 would make the original function that I started with undefined. So I'm going to substitute 3 into all of the x values. And I'm going to get in the numerator negative 1 times 2, which is negative 2. And in the denominator, I'm going to get 4 times 1, which is 4. So the hole will be located at 3, comma, negative 1/2. Now, to figure out where the x-intercepts are located, I'm just going to look at what values of x would make the numerator 0, because when the numerator of my rational function is 0, the entire function will be 0. So I believe that will be at x equals 4 and x equals 1. So I will have x-intercepts at 4, 0, and 1, 0. And to find the y-intercept, I just need to evaluate f of 0. Notice I'm using the simplified version of the function. It's going to be a little bit easier. So in the numerator I get negative 4 times negative 1, which is 4. In the denominator I get 1 times negative 2, which is negative 2. So it looks like the y-intercept is at 0, negative 2. Kind of running out of space here. I can squeeze it down here. Now the end behavior asymptote, Miss Adams did a video on end behavior asymptotes earlier. You want to think of the degree of the numerator and the denominator. Well, if I multiplied out this whole numerator, I would get a quadratic. That'd be degree 2. And if I just thought of the multiplication, I have an x and I'd get an x squared, a 1x squared in the numerator. And the same thing in the denominator. The denominator is also quadratic. I would get an x squared if I multiplied out those two binomials in the denominator. So the numerator and the denominator are both degree 2, so you look at the ratio of the coefficients, and it would just be 1x squared over 1x squared. So the EBA is just going to be y equals 1. And for the vertical asymptotes, you want to look at what x values would make the function, the simplified version of the function, undefined. So it looks like I've got an x plus 1 and x minus 2 in the denominator, so if x was negative 1, the function would be undefined, and if x was 2, the function would be undefined, so those are the locations of the vertical asymptotes. Now I'm going to put all of this information on the graph down here. So I'm going to zoom out a little bit, see if I can keep the graph and all of the information on the screen at the same time. So I'm going to dash in my vertical asymptotes. I've got one at negative 1, and 1 at 2, and the function will never cross over those vertical asymptotes. I've got an EBA at y equals 1. Remember, the function is not defined, is not undefined, rather, necessarily on the EBA, so the function could cross over the end behavior asymptote. That's okay. It could. It doesn't have to, but it could. Now I'm going to plot some of these points. I know I've got an x-intercept at 4, 0, and a y-intercept at 1, 0, and a y-intercept at 0, negative 2, and a hole at 3, comma, negative 1/2. That would be like right there. But I want to make sure that looks like a hole and not a point on the graph. So make that an open circle. And now I'm going to start to sketch my graph. I know the function can't go through, can't cross over the vertical asymptotes. It levels off at the end behavior asymptote. But now notice here right in the middle, this is kind of what I was talking about earlier. Function's got to go through those 2 points, and it's got to get close to those vertical asymptotes, so it happens to cross over the EBA there, and that's totally fine. So now the function doesn't have any more zeros, so I know the function's not going to cross over the x-axis any more times. So that means that the remaining part of the function is probably going to be up here like so. And if I wanted to get some exact points over there, I could make a table. But that's pretty good for the sketch. So you can see these are kind of layered and nuanced problems. You've got a lot of pieces to deal with here. You've got a lot of factoring to do, and then the chart is really helpful because it sort of organizes all of your information. It's a nice graphical organizer.